Good afternoon, everyone, and welcome to the third CLAS AI workshop this semester. We put together this series to help inform faculty, students, and staff in the college about recent developments and issues and techniques and methods in AI, which may be of particular interest to them. We are the home college to the data science degree program. We have a lot of faculty, I would guess the majority of our faculty, who spend quite a bit of their time in data. And as such, we very strongly embrace the idea that AI is going to have an impact at various times and in different ways in virtually every field within our college in the near future. And so I'm very pleased to welcome George Mikulitis today. I will ask Chris Mikulitis to do the introduction in a moment. I would just simply point out that George is the director of the Informatics Institute. And to show you how versatile he is, he actually runs his own AI seminar series, symposium series. And so we're very pleased to have George from our statistics department to give us a discussion today. And I'll turn the floor over to Chris Mikulitis to introduce Dr. Mikulitis.
Thanks, Dave. It's a pleasure to introduce George Mikulitis, who, as Dave mentions, a professor of statistics. He's also the director of the UF Informatics Institute. I met George about 6 years ago when UF created the Institute, and I was part of the search committee. And I remember George's interview, and I asked him a question whether or not big data, at the time we all talked about big data, whether big data had to be voluminous data, and he said no. Big data can be complex data. So point of that is that I think in the College of Liberal Arts and Sciences and around the university, there's all sorts of data that we have, may not be giant data sets, but they're data sets that are amenable to data science and AI. And through George's efforts, I think he's welcomed lots and lots of, and supported lots and lots of research in that area. George also was doing research and articles on machine learning before machine learning was cool. So today he's going to talk to us about, I think, the intersection of data science and AI, and I believe he's going to talk a bit about sort of primer on machine learning. So the way we'll do this, he's going to give his talk, which I think is around 40 minutes. And then you can go ahead and enter any questions in the Q&A at the bottom of your screen. And then when he's done, I'll moderate those questions. So let me turn it over to George.
All right. Good afternoon, everybody. Thanks much, David, for the invitation, and thanks to Chris for the kind introduction. And I think already both David and Chris have touched upon a number of keywords that I'm going to also talk about. This is not a very technical talk. It's trying to provide sort of a broad overview of data science, somewhere there is machine learning, AI, and some developments, both from a historical perspective and then leading to some open challenges that, to a large extent, define research agendas for the next possibly 5 or more years, and people are already actively working on them, even among UF faculty. So let me start with a preamble that many of you have already heard, and you're already working on some of the very recent investments that the university has made in the space of artificial intelligence, especially with the new Hypergator AI, and additional hiring in that very specific space, and also in data science. As David mentioned, the college is the home of the new data science major, co-directed by statistics and mathematics, and with a number, of course, from computer science. And all these developments occurred sometime in 2019, 2020, but actually investment in data science, as Chris hinted, go further back when the university put together the Informatics Institute, whose focus to a large extent is on data and computational enabled science and engineering. So there have been a number of investments, and it has been a very exciting time. And what I would like to do is walk you through some of the recent developments and also have some flashbacks to history. All right. Whenever you attend a data science workshop or a summit on data science, there's always that discussion whether what is data science, how you define it. There are various different definitions, but definitely in my mind is a field of study. As I've already mentioned, you have launched a major this year, so definitely you can get a degree. For those of you that have looked for jobs broadly in that field, you have noticed that there is a very high demand for jobs, and there have been a number of reports from federal agencies and also from private companies that canvass the job market about how hot data science jobs have been. And this is from a recent report from IBM, and which is freely available, and you can look at the detailed data afterwards. And the other thing, coming from an academic environment, definitely the federal agents and the federal government have put a lot of very targeted solicitations for research funding for creating an ecosystem of research around data science, both on the foundational level, but also how it interacts and with various scientific and engineering problems. So at a very high level, without making the very, very precise definition, data science is the study of extracting knowledge and value from data, and many other terms that we're going to encounter during this presentation, I view them as part of the data science pipeline. So there was a few years ago, I don't know if you can see it at the bottom of the screen, a leadership summit of directors of data science and related institutes that I attended, organized by the National Science Foundation. And at the end of the day, there was this report that started talking about the data life cycle. And you can see essentially the whole pipeline, and which starts with generation of data. And this, especially these days, with a lot of devices, it's very easy to get a lot of data. Most of us, we think of our cell phone as a means of communication, but at the same time, it's also a sensor. It can capture pictures, so that's a sensing device. It can capture our movements, if you have those mobile health applications, and so on and so forth. And therefore, essentially, all similar sensing devices in our homes, in our offices, smart buildings, and so on and so forth, generate an enormous amount of data, in addition, of course, to scientific instruments and other means of data generation. On the other hand, data generation doesn't mean automatically that everything is stored for further analysis. And that's a small difference between generation and collection, because on many occasions, as Chris mentioned, a very large volume of data may require to store either portion of them, those that have the highest value, or start going into compression type of techniques in order sort of to reduce their volume and then keep them for further processing. That brings us to processing, and that has to do with very elaborate pipelines, again, depending on the nature of the data, how they were acquired, their spatial temporal granularity, and so on and so forth, in order sort of to prepare them for further analysis. In many cases, what people are analyzing, or what eventually we're gonna use various techniques mentioned later on, are not the raw data, but a processed version that has undergone curation, cleaning, and so on and so forth. And then we come to aspects that involve how you store and manage the data. Some data need to be always available. Some others you can sort of retrieve them at a more leisurely pace for analysis. So these are sort of, how you organize and manage the data, topics that the computer science field has looked for a number of decades now. And then that's where data science, machine learning, AI statistics, my field, come strongly into the picture when we start talking about analysis techniques. And of course, analysis is not the end of the data life cycle. At the end of the day, you would like to interpret the results, visualize them, and then communicate them to the various stakeholders, whether they are your scientific collaborators or policy regulators or the general public. And of course, this sounds like a very streamlined linear process. It's nothing but a linear process. There are many feedback loops. On many cases, you go into little circles, you do some analysis, and then you go back to reprocess some of your data. And especially there is a continuous cycle between interpretation, communications, and further analysis. And what I'll mention towards the end of the talk is that obviously privacy and ethical concerns that permeate this cycle. And there was a very interesting presentation at the previous workshop by Professor Purvis from the Philosophy Department on Ethics and Fairness in AI and data science more generally. So emphasizing a little bit the field that I'm most familiar with and I have worked on, the analysis piece. Essentially, we're talking about different models, methods, algorithms, and it leverages a number of tools from various fields that are well established both within the college and other colleges. Mathematical modeling, probability and statistics, optimization techniques, ideas from information theory, control theory, and so on and so forth. And of course, that's where some of the confusion comes about, because depending on when people were thinking about or working on these analytical techniques, different names were en vogue. So probably the last 15, 20 years, machine learning has been a dominant term. The last 5 years, as we're going to see, artificial intelligence has become a very popular term, although that goes back more than 60 years. Earlier on in the 90s, when I was a graduate student, data mining was a very popular term. Statistical inference has a very long history going back to the 1930s. Later on, there was pattern recognition and so on and so forth. But all of them essentially capture different facets of this broad space of models, methods, and algorithms. So, as I mentioned, one of the most popular terms the last 5 years, a little bit longer, has been artificial intelligence. And I venture to say that it has become the mantra intoned by both academic people, obviously technology people, business leaders, politicians, journalists, and even the general public. And of course, historically, the term, as I've hinted, was coined a long time ago, sometime in the mid-50s, referring to the aspiration of realizing software and hardware an entity possessing almost human-level intelligence. So doing a flashback to history, this is where essentially the term artificial intelligence was coined back in the summer of 1956. And essentially, it was a gathering of researchers from various fields, and the key participants or the key contributors were John McCarthy, who was a young assistant professor of mathematics at Dartmouth, Marvin Minsky, cognitive and computer scientist at MIT, Claude Shannon, who was at the Bell Labs back then, the father of modern information theory, and Nathaniel Rochester, who was a researcher at IBM, who developed the IBM 700 computer series, and some other participants. And essentially, there were a number of developments at that point, and they wanted to see how they can move the field forward. And one of the reasons that John McCarthy chose the term artificial intelligence, he wanted sort of to differentiate from another very dominant term back in that era, cybernetics, but was used by the great MIT mathematician Norbert Wiener. And therefore, he didn't want it sort of to get into conflict, and there were some other issues. So a little bit on the history. And of course, since then, there has been a roller coaster of success and setbacks. As usual in any new research endeavor, people set up very high aspirations, and sometimes they set the bar very high, and eventually there are either intellectual or more practical roadblocks that take a number of years, sometimes decades, to overcome. And one of many of the setbacks that occurred over the last 60 plus years to make progress were inadequate computing power. I mean, the usual claim is that the computational power that your cell phone has today exceeds the computational power of many supercomputers 20 or 30 years ago. Therefore, you can see that in order to realize this research program, computing power was of the essence, and back then it was not adequate, and even 20 or 30 years later on in the 80s, it was still not adequate to realize sort of the full potential of what artificial intelligence could do. Nevertheless, there were also a number of many big successes, and my argument would be that they came about by focusing on looking at more well-defined problems, but involved making well-founded predictions, testing scientific hypotheses, and therefore further developing that framework, and also making data-driven decisions. That's where essentially, it's not only how we use the big data or the large amount of data, what models we use, but how we can also use them for decisions. Actually, I found out that, as it says at the bottom of my slide, the Wikipedia entries on the history and timeline of AI actually provide a very good overview if you would like to take a look. However, some of these successes, essentially, they are what these days, or until recently, people were calling the field of machine learning. And essentially, they were aided by coming up with new ideas and especially expanding our algorithmic toolkit. So let me switch gears a little bit, and as Chris hinted at the introduction, let me talk a little bit about machine learning, something that many in the audience may have taken courses at the university, or many in the audience may be teaching such courses. So I'm taking the definition out of Tom Mitchell's book. Tom Mitchell is a computer scientist at MIT that says that what is machine learning at a very abstract level is the study of algorithms that improve their performance at some particular task based on some experience. And I'm going to discuss briefly a couple of examples on the next slide. So you can see that in this case, you can, although despite the abstractive nature of this definition, you can start thinking about well-defined learning tasks through this triplet. So let's look at a couple of examples. Many of you will start recognizing that these fall within the realm of predictive analytics. So let's say that our task is to recognize handwritten digits, and the performance criterion is what percentage of digits our algorithm will correctly classify. And then what is the experience is all the data that we have collected of human labeled images of such handwritten digits. So in that case, we have the experience, the performance criterion, and the specific task. Another one may be For something much more complicated, like automatic speech recognition, and again, you can analogously define the performance criterion and what the experience is, where you're going to find the data. I don't want to spend much time on sample applications. Applications of machine learning are everywhere. I started by recommendation engines because these have become very pervasive in our daily lives. We have recommendations when we watch movies, or we watch any social media platform, or when we watch videos at home as part of the entertainment. Our shopping experience comes with recommendations. When all of us will be able to go back more often to restaurants, they also come with recommendations through various platforms and so forth. Turn to something somewhat different: personalized medicine, drug design. We have seen a lot of big successes. Obviously, the field of image and video analytics, computer vision with numerous applications. A topic of a previous webinar offered by CLAS on natural language processing and text analytics and speech recognition, autonomous systems. The biggest success in the next few years are self-driving cars, and the list goes on and on and on, and covers various scientific and engineering domains with applications that impact our daily lives as well. So let me spend some time talking at a very high level, very briefly, about an overview of learning tasks. This is almost like the first lecture on a machine learning course that many of you have taken. So in principle, I've put them in 4 categories: supervised, unsupervised learning. I'm not going to talk about semi-supervised learning, which is a combination of the first 2. And then a few words about reinforcement learning, because that's where big data and algorithms meet decision making. And actually, it's a very old field. It goes back to a lot of ideas from control theory with some modern twists. So actually, in terms of supervised learning, on the webinar on natural language processing and text analytics, the speakers hinted at some of these ideas, and in many of your classes you may have also encountered supervised learning techniques like under the names of regression and classification. And the problem statement is very, very simple. You have some training data. Think of the experience in the previous definition, a database of images of hundreds and digits, for example, and the images, of course, then you need sort of to break them into appropriate features that you can process on the computer. And the output, for example, for the 100 and digits are 10 classes from 0 to 9, the 10 digits. In other contexts, may be a numerical output. You may want to predict the sales, a company may want to predict its sales volume, and so on and so forth, or you may want to predict survival time for patients suffering from a particular disease. And the objective is to learn a function of the inputs to predict the output. So again, I'm not at all precise, but essentially the goal is how to learn these functions so that you can map the inputs to the outputs, and this mapping has a good performance. In the case of the 100 and digit recognition, is to predict correctly based on the features that you can extract from the image, the right digit when you present it with just an image. So the computer essentially, if you're successful in this endeavor, you learn a good function, then you can sort of use the corresponding algorithm and automate understanding and reading all these digits. And of course, the performance of the function that you've learned, that's why I put the hat. This is what you learn from your training data, is assessed in most cases on an independent test data set. And here I have 2 examples of such functions. Here they were data, two-dimensional data. It's kind of a toy example. And there were two classes, the green class and the blue class. And you can see that in this case, essentially, you had a linear function separating the two classes, whereas here you had kind of a quadratic, a more complex type of function. And this gets us to a very, very, very big topic where there is a lot of current interest, because one type of functions that people are using for this type of tasks are neural networks, where in some cases, they have become synonymous with modern AI. Maybe some in the audience may slightly disagree, but definitely neural networks are at the core of modern developments or recent developments in artificial intelligence. So what should this representation be? And a lot of these ideas, obviously, simple functions like linear or polynomial functions go back even before the 1950s. Symbolic functions like decision trees came about in the 80s. Nearest neighbors were a little bit older from the 60s. The same with probabilistic models. So you can see that just coming up with ideas of what should the representation of this function be in order to be able to do supervised learning, it's a topic that people have been studying and coming up with new ideas for over 60, 70 years now. And then once you have decided on this representation, this opens another big area of study. Which algorithm are you going to use to learn the structure of this function? And I'm going to give a couple of examples on the next slides. Then there are, so this goes about the representation, but then there are other more subtle issues that on many occasions when you develop the algorithm, on some occasions, people originally disregard, but then you need to start thinking about those. Were the inputs and the output random samples or sums of convenience? So for example, we went out and we took images around campus. This is maybe not be a random sample of all the images that you can take around all campuses across the nation. So does this have implications of how you train your algorithm and what results you're going to get? Do you start having implicit biases? Okay, right now, if we're talking about pictures of buildings or trees around campus, that's one question. But the input data, and they may have been characteristics of job applicants, and the learning task was to have an algorithm that's going to make recommendations about hiring. So suddenly, this issue and the potential of having implicit biases becomes super significant. And we're going to touch a little bit upon this issue towards the end of the talk. And then a little bit more of a technical issue: if these random samples were independent, if there are exhibit dependencies, then there is a subfield called collaborative classification. Then if the random samples came for the training data where you develop your algorithm and its representation came from one particular distribution, but then the distribution shifted. Think of the handwritten example. Let's say that the distribution of the digits was collected by one set of people that wrote down all these digits, and that had a particular way of writing them. And then your test data set comes from a different set of people that, tilt the image, or the way they write the digits is somewhat different. So in that case, you have a shift in the distribution, and then other ideas come to the fore, like transfer learning. And then, of course, what is the performance evaluation criterion? Obviously, accuracy, how many digits you have accurately, your algorithm has accurately predicted, is the first that comes to mind. But at the technical level, people have explored all these other possibilities. So my point is that the problem is very easy to state. It addresses a number of very important scientific and other problems, but at the technical level, it becomes very rich, and it has a number of implications and a number of nuances. And the community has made a lot of progress, but especially when we start coming to very complex models, some of these issues are at this point topics for active research. So a little bit more on some of these representations. I've mentioned, you know, a linear function, that's easy. Essentially, you just need to learn the coefficients beta j from the training data. Here is a simple neural network, the simplest possible neural network that you can think of. Actually, it was discovered back in the early 60s. It only has, here are the inputs, the original features of the problem, the xi's. Here are the outputs, the different digits that you would like to predict. And then the neural networks have, you know, this hidden layer that essentially start, as you can see, taking linear combinations of your features. You know, they may shift them a bit, and then they process them through what is known as the activation function. So that starts giving you a more rich set of functions to try to map the inputs to the output. If you take it to the next level, so in this case, the learning task is, and your algorithm needs somehow to learn the weights W and the shift B. But if you start putting many more hidden layers, how do you do that? And some of the big successes have come with algorithmic breakthroughs of how you can extend, you know, this idea. A couple of hours ago, we had in the informatics seminar series on artificial intelligence, we had a presentation about artificial intelligence and biodiversity. And a lot of the applications were on images of species. And therefore, the whole presentation was about convolutional neural networks at the technical level. I'm not going to try to explain all the details. Here is a standard picture of how, you know, the basic building blocks of a convolutional neural network, but suddenly you realize that this has become an order of magnitude much more complex, both to train and also to interpret. You know, if you have a linear function and you see a big coefficient here, you start thinking that maybe this feature is important in some shape or form. Maybe here you may be able sort of to peer through the hidden layers and start getting some intuition of what's going on. Here things become much, much harder. And then there are other flavors of neural networks, like recurrent neural networks, generative adversarial neural networks, residual neural networks, and, you know, people keep coming up with more fancy architectures. So why neural networks? And I would like, again, a history flashback. Most of you may be aware of this, the Alexnet back in 2012. So the background was that the computer vision community had created that ImageNet project, which is a large visual database designed for a competition. And essentially people were designing algorithms to recognize the object in the image. And there was, all of them were hand annotated. That was a lot of work by the community, and a lot of them had extra features that you could use. And essentially, it contains something like 20,000 different categories. In the toy example that I mentioned about handwritten digits, there were 10 categories that your algorithm had to recognize. Here, obviously, this is a much bigger task. And at the first two instances of the competition, there were a number of algorithms, and then the misclassification error rate was about 25%. Essentially, the algorithms could get 75% of the images. And the same, so that was the case for the first 2 years. And then Alexnet came along, which was a convolutional neural network that only misclassified 15% of the images. And as they say, the rest is history. It was designed by Alex Krzyzewski. That's why he gave his name. And right now, everybody knows about Alexnet. He was a PhD student of Jeff Hinton, who was together with two other pioneers of modern artificial intelligence and deep learning, Jan LeCun and Joshua Bengio, recipients of the 2018 Turing Award for their contributions, not only conceptual, not only algorithmic, but engineering of how to use GPUs, of making deep neural networks a critical component in computing. All of us wish that we had such papers with that high number of citations. But the key thing is that by 2017, essentially the majority of the algorithms have focused on these deep neural networks using various layers and different ideas from convolutional neural networks. And some of the top performers have gone from a few layers, which was the case for Alexnet, to over 100 hidden layers. And again, if you have an image classification task, it may not be as important to understand and interpret what the underlying algorithm is doing, as long as it has high performance. But when you use, let's say, such a complex architecture to predict, to do medical diagnosis, it may be more comforting if at least there is some interpretability. And I'm going to come back to this theme. Very quickly, before we go to some open challenges, talking about unsupervised learning, essentially a number of things that you heard on the previous webinar on topics models in natural language processing come under the broad topic of unsupervised learning. You're trying sort of either to reduce the dimension of your data or do some clustering. Here I'm having a particular clustering example where you had molecular data and you're trying sort of to organize them according to the biomolecules being profiled, and also organize the samples in order to see if there are appropriate groupings, and you see some very nice structure. Switching very quickly before I go to some open challenges, reinforcement learning is essentially what's behind some of the successes of algorithms that became world champions in chess, the big success of AlphaGo that came out of DeepMind, the Google subsidiary, and became a champion, world champion in the game of Go. And essentially, here I have a typical example from robotics. You are sort of trying to control the motion of a robot arm in, let's say, in repetitive tasks, and you may have some additional requirements that the movements are not too jerky, they're fairly fast and smooth. So essentially, in a reinforcement learning at a very high level, you have information about the environment. These are the states. And based on that information, you can take actions. And in this example is you regulate the underlying motors of the robot. And anytime you have a success, you get a positive reward, and potentially, to, for example, address bullet point 2, you may also introduce some negative reward. So essentially, reinforcement learning is, that's where the term comes from, essentially based on observing the environment, taking the action, seeing the reward. The goal is to maximize a long-term reward function. And this is called a policy, but is essentially a mapping from stage to actions. And essentially, a lot of ideas currently employed in robotics. I mentioned about AlphaGo and chess type of algorithms essentially use this type of framework. Autonomous cars are also heavily rely on similar frameworks, of course, together with some of the previous supervised learning tasks of understanding the environment and doing the right predictions and so on and so forth. Okay, in the last few minutes and the last few slides, I would like to discuss a little bit about open challenges. And here is by no means an exhaustive list, and I've colored it in different colors. The blue ones refer more to open research tasks. The orange one refers to computing issues and infrastructure. And the last four touch upon broader issues, Many of them have very technical underpinnings in order sort of to address them, but obviously, given how popular and how embedded in our daily lives many of these algorithms have started becoming, and especially given the huge successes of deep learning algorithms, at some point we need sort of to think hard and address many of these issues. And there is a lot of ongoing research, including at UF. So a little bit on the more technical aspects, as I've already mentioned, if for your predictive analytic tasks you had a simple linear function, it's very easy, it's very transparent, and both from an interpretation perspective, but we also know why it works, and we also know when it breaks down. There has been a lot of research over the years, and that's where we stand. On the other hand, the moment we go into these very complex algorithms like the convolutional neural networks, recurrent neural networks, and so forth, there's definitely limited understanding of both the mathematical properties and other computational information theoretic limits. We don't have a good understanding of the robustness or fragility to the training data. If we change a little bit the training data, we may see what's going to happen, but we don't have a principled way of understanding why some of these things happened. There is progress, don't get me wrong, but we're not there yet. And of course, understanding how the results look like. My emphasis when I discussed supervised learning was primarily on predictive tasks. That's where a lot of algorithms over the years have seen huge successes, and especially the last few years, deep learning algorithms. But in many other domains, you are not only interested in predictive tasks, but also sort of understanding relationship between cause and effect from observational data, and also understand root causes of outcomes, and also possibly enable modeling interventions. I think a lot of, you design, if you're a policymaker, you design a particular intervention, for a school or for a neighborhood. At that point, it's not just a predictive task, but you would like sort of understand what happens within a more causal reasoning framework. And again, in statistics, there has been a lot of work and a lot of progress. If you use simple linear models, but extending to these more complex models, that's much more open. Something else that a number of people at the university are working on is a lot of these models that I've described are completely data-driven. You have this training data, you have a task, and essentially you come up with the functional representation F. Nevertheless, there is, for example, in David's field, chemistry, there is a lot of physical or chemical laws that govern experiments and so forth. So the question is, how do you integrate knowledge in a principal framework that comes from such physical laws? In other areas, there might be theories or principles with data-driven models. And again, data are not nice and homogeneous. They may have been collected, as I mentioned, in different instances, under different environments. So how you do this integration from heterogeneous data sources. The key point here is that all of this require close and deep collaborations between domain researchers and technologists. A few words on computing infrastructure. In scientific computing, there is this well-established notion of co-design between hardware and algorithms. And at some point, that's where the field of both data science and AI will move to. And here there are a few examples. And then let me touch upon some other issues that are not at the more technical or infrastructure aspects, but start touching about how we use these algorithms, how we trust these algorithms. At a little bit more narrow level is the issue of reproducibility and replicability. And for those of you that would like to read more, essentially a number of these few things mentioned on this slide come from this very recent report from the National Academies. Obviously, we need to have data reproducibility, analysis reproducibility, and stability. You know, if I change a little bit my input data, my results and my analysis results should not look completely different, and also whether the results are also can be replicated and reproducible. And this covers both infrastructure, you know, in order to have data reproducibility, how the data were processed. So if I'm processing the data, suddenly I don't change something fundamental in the nature of the raw data, and also other mechanisms of how we build, you know, these community processes about mechanisms for sharing models, results, and procedures to assess replicability. You know, there have been a number of papers, those of you coming from psychology and from the health sciences, where important results could not be replicated, and there are a whole bunch of reasons that it's a topic for another webinar. But as everything becomes more complex, this comes to the fore. I've already hinted at some of these topics on trustworthy and interpretable machine learning and AI. As you have seen with this very brief presentation, many of these models are very complex and opaque, inherently probabilistic, and you know, many cases depend on the data, but they are used both on training and where they were applied to. And on many of them, for maybe for some tasks I've already mentioned, having a very interpretable model may not be as important as for other tasks. Recall the example of recognizing a digit versus making hiring decisions. Because otherwise, especially, you know, as more such algorithms are adopted, we need sort of to build trust on them. And the audiences are multiple. It's obviously the technical audience that develops these models and algorithms, the customers, but also it touches upon policymakers, regulators, consumers, and us as a general public. In the previous webinar, Duncan Purvis covered very, very well the issues of privacy, you know, how you both at the technical level and other broader considerations. And of course, it's a very active area of research with a number of technical developments. And again, I'm relying on Duncan's presentation on ethics and fairness in AI. You know, he gave both a presentation at the Informatics Institute seminar series and a webinar where he touched upon all these issues, and he gave some great examples. Regarding the algorithm, this is a very recent book from two computer scientists at UPenn talking about the ethical algorithm and touching upon a number of issues. And definitely privacy, trustworthiness, interpretability, and ethics and fairness are huge areas that impact every facet of data science and AI, and more progress is needed at all levels. And of course, engagement of the broader public. So in the last few slides, a few remarks on education and training. If I were to revisit my original slide on the data life cycle, we need, as we educate our students, they need to build some expertise about the domain and the technology used to acquire data. You know, once you start having a feeling for the data, you can also potentially have a deeper understanding. And of course, that's going to be helpful in the last step of how you communicate the results. You need to have some understanding about the domain. But at the same time, as you have seen through this brief presentation, they need sort of to develop expertise at different levels, depending on their interest in computing, algorithms, modeling, and inference skills. And essentially, this touch upon different other foundational areas. So this is my very personal view, but the educational programs need to cover foundations to equip students with this good expertise in computer algorithms and modeling skills. However, as you have probably noticed, data science and machine learning and AI have enormous breadth and depth, and therefore you cannot design a program, an educational program to cover everything. So essentially, all of us have to become to go into continuous learning, learn about recent developments, and this can be done through other mechanisms like short courses, workshops. The Informatics Institute, just to advertise what we do, has a very active program of short courses and workshops on these topics. And of course, I cannot emphasize enough the importance of lab rotations, where you get in touch with the domain experts, and also for the students to go after internships. And as the mantra goes, the best way to learn data science, ML, and AI is do it actively by working on specific problems. There has also been, at the very introductory level, some innovation. I promised Chris to talk, or at least to mention Data 8, not because the reason is it's offered by UC Berkeley, and you can go and check it on the web. But when it came out, it showed, even for freshmen with no experience in programming, no previous statistics course, how you can start introducing key ideas about computing, about thinking about data, doing something with the data, start thinking about the stochasticity, the randomness, and all these issues at a very early stage. So that has essentially motivated the community to come up, and many other universities by now have designed similar courses. That's why my belief is that it forced the community sort of to think hard and try to see how we can take a very new view rather than sort of going through much more traditional routes. Okay, you need expertise in computing. Okay, take a course in computing. We need some expertise in statistics. Start taking a course in statistics, and then we're going to integrate. So that changed the thinking of the community. And on my last slide, I would like to finish that this is a very exciting field. There is, after many, many years, we're talking a very common language. There is convergence from multiple fields, ideas contributing from multiple fields in the research communities, working on common problems and tasks. And I cannot emphasize enough that there needs to be a very deep engagement and strong collaborations between domain experts, technologists, and broader stakeholders. Thank you very much for your attention. I hope we have some time for questions.
We got a little bit of time, and I'll get to it. There's one question asking you to elaborate on the difference between machine learning and deep learning.
So if I were to go back to this slide, a lot of these other functional representations that go back from the 60s, the 70s, up to 2010, or very shallow neural networks, these were what we were calling machine learning. The key idea of deep learning is you start designing this algorithm and then you go 100 layers. And there were two issues in order to realize, people may have thought about that, but there were big challenges to realize those. How you train them, what are the algorithms, and also how do you do it efficiently on hardware? And that's where some of the key contributions of Jeff Hinton and the other folks came about. It was not only about thinking about the algorithmic issues and also some conceptual issues, but also about the engineering breakthroughs.
Okay, here's another question. Is AI effectively overhyped? So there is some sense that it is just an extension of some things that we were natural progressions, right, of what we were already doing in statistics and computing. So what's special about AI that isn't just, more advanced statistics, more advanced computer science?
Okay, that's a really tricky question. And I'm not going to venture a very definite answer. But going back to a little bit this slide, there have been a number of surprises, not only in terms of performance, these very good performance on particular tasks. But the last couple of years, people have started sort of digging under the hood to understand how these algorithms learn with these very complex architectures. And, something that in any classical statistic course, you learn about the bias variance trade-off, whatever that is. Suddenly we don't quite see it. Maybe it's there, we don't quite recognize it, but to many of us that has, and to the community, has come as sort of a surprise. So there have been a number of surprises. Again, I'm not gonna venture about what's gonna happen in the future. As I've mentioned, it has been a roller coaster of big successes and a number of setbacks, but right now with the advancements in storage and computational power, there have been some huge breakthroughs, and there is a proliferation of new ideas. So I think we need to be optimistic.
There's a question. So getting back to the sort of deep learning, the notion is that the next step from machine learning is deep learning. And the question is, can you speculate on what the next step is from deep learning to what?
No. It's, there are, okay, Jeff Hinton, who, that I've already mentioned his name, gave an interview actually a couple of weeks ago. I think it was at the MIT Review, and said that right now we are reaching the very, very complex architectures that some of the goals that the pioneers back in 1956, the big broad vision that they had, may be realizable within the next sort of 10 years. So the next step will be sort of to go back to not human imitative AI, where you have very well specified tasks where we have had tremendous successes, but trying sort of to get much more to reasoning the way we humans do. How far we are from there, there is a lot of speculation. I'm a much more technical person. Some of these issues I don't fully understand them myself, but in the meantime, what's going to be much more important is this issue, trustworthiness and interpretability. Because as these complex algorithms start permeating all facets of our daily lives, and at some point, and given their inherent biases for various reasons, if they are not interpretable, or at least we have some idea of what they are doing and why maybe they produce non-fair outcomes and so forth, if the public starts losing trust, then there's going to be a backlash. So I think it has very, very broad implications, but at the same time, it also poses very specific technical questions that the community needs to tackle. The two go always hand in hand, at least in my view.
Let me ask you one more quick question. It's probably not quick. So the notion of intelligence is a biological cognitive function that makes task assignment and then decides how to do task improvement. So how do people in your area view intelligence? What does intelligence mean in the artificial intelligence context?
I think I've already hinted at where we stand right now. Maybe members in the audience coming from other fields may disagree, but to me, at present, we have solved, these algorithms are solving very specific tasks that sort of imitate human intelligence, predicting an image, doing this, doing that. The question is very deep, and I don't think I'm the right person.
You're already out of time, so.
Yeah, to answer it, and that's sort of the next frontier, and that's, I think, how high the bar is. To be honest, I don't really know, but at some point, that's where we would like to go. Just one last remark for people that have looked at all these algorithms based on these complex neural networks that play chess or Go and so forth. At some point, they started getting a little bit surprised because many games that this algo is played were very orthogonal to how a chess grandmaster would have played it. So at that point, there is something more going on by just having a lot of computational power and sort of imitating based on experience of all the other chess grandmasters. So that's just as a factoid, but there might be something very interesting happening there, but I'm not the right person to answer that question.
Okay. Well, thank you, George. That was an excellent talk, and very much appreciate your time.
Thanks everybody for attending.
Yeah. Okay. Thank you all. Thank you for participating. We'll see you next time.